What I want to talk about today is impact, and it's more directly related to linear momentum. And it's one of those things that we sort of skirt around a little bit in the course, but it's worthwhile to know about because you're going to end up with questions later on if you do any type of co-op or final position. You should recognize what this is. So what I'm trying for here are two learning objectives, or two main learning objectives. What happens when two particles come into contact. I want to discuss the types of impact and introduce the idea of the coefficient of restitution. And the coefficient of restitution in particular is not normally covered in the live lectures, but it is something that we do cover, I do cover in these video lectures, and I'm including it as sort of a supplemental piece of material. So what happens when there's impact? When you have two bodies collide, during a very short period of time, there's a relatively large impulse between the two bodies. And so if you think about it, we often talk about the kid hitting the baseball and the bat and the ball being in contact for an infinitesimal amount of time. And that translates to a momentum. But you can be a bit more specific. So the first one type of motion is central impact, which is the direction of motion of the mass centers of the two colliding particles is along the line of impact. So I'm just going to show you what that looks like. So that's two balls coming together, for example, and they come into contact at the center. And I'll define in here a couple things, which are the line of impact over here and the plane of impact over here. So plane of impact is where the impact is occurring. The line of impact is just the line over which that action is occurring. Oblique impact is a little bit different. One or both of the particles is at an angle with the line of impact. And so, for example, here you have two particles that are traveling off at different directions. So they're going off in these two senses. And you have to be aware of that as we sort of define things. All that oblique impact really does is it adds in a second dimension. So if you play pool, billiards, you need to think about direction and velocity of the particles after impact, same thing. And so, you know, you want to go down to a pool hall after this lecture and say it's part of your dynamic study. So I'm trying to see whether this will work. I did a very simple case of a tennis ball, and the tennis ball is released, and you'll see that it bounces up and down. Now, one of the things you should notice is that in the bouncing, I started up here, but on the second bounce, it only went that high. And then with each subsequent bounce, it sort of goes a little bit lower in terms of the maximum height. And so what determines the quality of tennis balls? And so tennis balls are pretty easy. Why isn't the bounce 100% of the original drop height? How can we use this type of information? And what does this do in terms of sort of informing engineering decisions and potentially forensics and all sorts of things as you go through and try to analyze accidents? So let's consider a central impact again. Two smooth particles, A and B. Both are moving with slightly different velocities, VA1, VB1, corresponding to the individual particle. They come into contact. VA1 is greater than VB1, so you kind of expect that to happen eventually. And there's an impact that occurs. And if you look closely at the previous video with the tennis ball that I just did, you'll notice that as it came into contact with the kitchen counter, which is where I did the rigorous scientific experiment, there was a slight deformation as it came into contact with the counter. And so it sort of flattens out and then extends. So the deformation period is dealing with an impulse. And that impulse is going to be, say, a vector force P, which is acting over a short time. So that's an impulse P delta T, or P dt. And that's the effect of particle A on particle B. However, because this is a system of particles and there are two particles together, there's an equal and opposite force, minus p dt. That's the effect of B on A. And remember, that kind of makes sense from Newton's third law. At the moment of maximum deformation, the particles are going to move with the same velocity. Relative motion between the two is zero. Remember, at the very beginning, VA1 and VB1 were different. Then, after, there's going to be a period of restitution. Particles either return to their original shape, so remember that tennis ball that I dropped, it formed back up into a nice sphere, or remain permanently deformed. So if I took a piece of silly putty and I whacked it against the wall, it would sort of agglomerate right there, or chewing gum, depending on how strong you are with sort of whacking those things on walls. And the equal or opposite restitution impulse, RDT, pushes the particle apart from each other. So that's the same thing. So R dt is positive in one direction and R dt is negative in the other. The deformation impulse is always greater than the restitution. You always, it's one of those things that you always end up paying for. And so paying for things is what engineers do. And you recognize that you have this effect every time you look at a particle. So this is the restitution impulse. And after this, the particles will have a final momenta where VB2 is greater than VA2. So afterwards they move apart, and particle A is going to sort of transmit some of the momentum into B, and B also. But in the end result is B is going to be moving ahead of A. And this is where we're kind of not talking about this in the course, but it's helpful to sort of define this. The ratio of the restitution impulse to the deformation impulse is the coefficient of restitution. And you can imagine that trying to extract out a sort of PDT and RDT is pretty hard to do on the fly. However, often it's more simple for someone to say, well, look, I just need to know the difference in velocities of particle B and particle A after impact and before impact. You'll also note that we kind of flip the direction of the terms. So VB minus VA, VA1 minus VB1. And again, I'll stress that in the live lectures we do not cover this. However, it really is important because I'd like to be able to define something like plastic and elastic collisions, and without this, things are lost. And so I think I find it's personally very helpful to me to have sort of this in the back of my head as I'm sort of looking at these concepts and not use them as just definition. Not surprisingly, the coefficient of restitution, E, can only vary between 0 and 1. Its maximum value, if you have sort of a perfect collision, is going to be that the difference between the two stays exactly the same, and you'll get E of 1. You can also have something that comes to a complete stop or something of that nature, and that goes to 0. So if the collision between two particles is perfectly elastic, the deformation is equal and opposite to the restitution impulse. And the nice thing is that kinetic energy is conserved as well. So that doesn't happen very often. I ended up sort of making a very bad slide here where I kept my M1s and or masses in the diagram. So you can see here, this is before impact and after impact. And the reason why I've defined the masses here is the mass of each of these is the same. The velocities of both of these are the same but opposite. And after impact, the same thing happens, same masses. Velocities are the same but opposite and in opposite to the original orientation. So in the plastic or inelastic impact, there's no restitution impulse given. And so RDT goes to 0. After collision, both particles stick and move with a common velocity. So here I was a little bit careless or careful and sort of said, well, it should be M1, V1, M1, V2, and probably better for the sake of doing this that I sort of define this not as M1 but M2, so I don't have any commonality between the two. But it doesn't really matter. In this case, I have a plastic inelastic impact, which results in a common velocity of both particles afterwards. So in the course, when we do this, often what we do is we don't define this in terms of elastic or plastic, but we tell you what the beginning and the end velocities are, and then you can calculate the impulse, and from the impulse you get some information about what kind of forces were involved. So for example, two trucks hitting each other, a ball dropping and bouncing up, that sort of thing. So we don't really talk about this in this kind of format that I'm doing here, but we do talk about it in the course indirectly. And again, this is why I'm sort of stressing it so much in this supplemental lecture. The other thing is, and I gotta sort of mention it again, oblique impact. Particles move away from each other with velocities having unknown directions, unknown magnitude, and 4 unknowns are presented in the problem. So remember, this is now two-dimensional motion. I have two particles that are sort of impacting, MA and B. They come in with one velocity, and they have a theta and a phi with respect to the horizontal. And after impact, they have sort of a different phi and a different theta. And so I have VA1, VA2, VB2, VB1, Phi1, Phi2, Theta1, Theta2, and I have the line of impact and the plane of impact in all of these cases. My equations just become MAVAX1, so, oops. I have the initial linear momentum. I'm going to write that out. Final linear momentum, and the impulse delivered. And it's in coordinate directions, x, 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 y, 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 for particle 1, particle 2, and I also have it for the other particles, MBVABX1 and BVBY1, but because, again, Newton's third law, both of these are separate, so, or opposite sense. I can calculate based on the geometry I'm given and the information in terms of theta 1, theta 2, what the velocities are for in the x and y direction for A. Same thing for B. I have phi 1, phi 2, and I can calculate the beginning and end velocities. Now, if the line of impact is just along that x-axis, that is, the impact occurs along that same line, there's clearly no y component, and I'll just erase it. So you can see here I've just sort of whited out everything through the magic of PowerPoint. So the only goal here, really define impact and coefficient restitution and set up how to solve these problems. You will see problems like this, but they won't be called coefficient restitution. They'll be called, well, the particles move off with certain velocity, come together at a certain velocity and move off with a certain velocity. You need to be able to solve these sorts of things. I think this is helpful to sort of visualize why exactly we're talking in this way. Thank you very much, and we'll talk again